So students, I hope everybody is fine. And what we would like to do in this video is we would like to actually use the normalization condition. And we have an example here that we have a wave function, and this wave function is defined by this equation. And what we have to do is we have to find the value of this an, and this psi is defined between 0 and L. So in solving this problem, in getting the value of this constant that appears in this equation, we can use the normalization condition. So this is my psi. What am I supposed to do first is to write down its complex conjugate. So complex conjugate. So what will be the complex conjugate? That will be psi star of x. Then this an star sine of 2 pi n x by L. So I have the wave function psi. I have written down its complex conjugate. Now, in order to calculate the value of this constant, the value of this an, I have to use the normalization condition. Normalization condition. Now, as we understand, normalization is from minus infinity to infinity, then psi star of x, psi of x dx, this whole thing should be equal to 1. Now let's use the value of the wave function psi of x and its complex conjugate in the integral. So what I'll have is integral minus infinity to infinity, and for psi star I have an star sine of 2 pi nx by L times psi of x, and that's an times sine of 2 pi nx by L. Then we have dx, this is equal to 1. As we understand that in the problem, the limit of this problem is given from 0 to L, so we can immediately replace these limits by 0 to L. So I will have an star an here, and I will have sine square 2 pi nx by L dx equal to 1. That should be the case. And what we understand that if you have a complex number and its complex conjugate, we would like to have its magnitude, because that will ultimately give us the number, a real number. So I can write down here an square integral 0 to L, then sine square 2 pi nx by L dx is equal to 1. Now for this we have a formula for sine square theta, and that is 1 minus cos 2 theta by 2. So we can use this formula in this equation. So what we'll have an square times 1 minus, this is 0 to L, 1 minus, this is cos of 4 pi nx by L. Yeah, this whole thing should be divided by 2, and this whole thing is equal to 1. So we have got the rid of square in the integrand in the above equation. Now, when we evaluate this integral, this whole thing, the integration of cos of this thing, giving the limits from 0 to L, we will get 0 for it. And what we will be left with is 1 by 2, 1 by 2x. So what we will have here is we will get an square. Yeah. So here we will have 0 to L, and here, because this is dx here, so we will get x by 2. This other part of the integration will automatically be equal to 0 when you will convert this into the sign, and sine of n pi will be 0, and this whole thing will be equalized to 0. So this thing is equal to 1. So this an square is L by 2. This is equal to 1. So this implies that this an square is 2 by L. So this implies that an is under root of 2 by L. So we have got the value of this constant an using the normalization condition. So what we have done is we have normalized this wave function, which was sine of x is equal to an. Instead of an, I would like to write 2 by L sine of 2 pi, what was it, 2 pi n x by L. So this is the normalized wave function, and we have calculated the value of this this constant an using normalization. Now let us take another problem and try to solve it. And now we have another problem here. And what we have is we have a wave function defined by e to the power of minus alpha x, and for all values of x which are greater than 0, and this wave function is e to the power of plus alpha x for all values of x that are less than 0. And what is important here is that this alpha is positive. It's a positive and it's a constant. So what we want is we want to have a normalized wave function, and for normalization, what I will have is for normalization. Okay, what I will have is integral minus infinity to infinity psi star of x psi of x dx is equal to 1. So this is the condition that we use for normalization. So for normalization, we have this condition that's important. Now, as this as the function this psi is real. It's a real function here. Alpha is positive and it's a constant. So psi star will give us the same value, and when a, if you take the complex conjugate of a, that will give us a real number when we will multiply the two a's. So what we should write down this whole function in terms of the normalization. So what I do is I would like to write down an integral for this region and then for this region, and I would like to add them and then try to find the value for this a, which is to be determined using normalization. Now, what should I do is that see, we have here x greater than 0, and then we have x less than 0. So I can start from this minus infinity. So I have an integral from minus infinity and it will come to 0. And when I will multiply the two wave functions, the psi of x and its complex conjugate, I will be getting here a star and e to the power of 2 alpha x, because when we multiply them, the base is same and their powers will be added, and then I will have dx here, and then the other part will start from 0. It will start from 0 and it will move to infinity for x greater than 0, and I will have the multiplication between a and a star. Here I'll have a star, which ultimately will be a real number, and then what we'll have is e to the power of minus twice alpha x dx, because when we multiply this psi of x with psi star, basis same powers will be added and we will have e to the power of minus 2 alpha x, and this must be equal to 1. Now this equation is very simple. We can integrate this exponential function in the easiest way. I don't have any number. Let me keep it 2. So what am I going to get after integration? So here I will get a square out, because a star will give me a square, and then I would like to e to the power of 2 alpha x. It will be same e to the power of 2 alpha x divided by the internal derivative of this 2 alpha x, that will be 2 alpha. So I would like to give the limits here as minus infinity to infinity. Then I would like to add it, and I will have another a square. Then I would like to integrate this e to the power of minus 2 alpha x. This will be e to the power of minus 2 alpha x divided by the internal derivative of minus 2 alpha x, that will be minus 2 alpha. And in this case, we will have the limits from 0 to infinity. We will have the limits from 0 to infinity, and I would like to close this thing, and this whole thing should be equal to 1. And that should be the case. Now, here we can have a squared by 2 alpha out, and what we will have here is here it has to be 0, minus infinity to 0. Then it is from 0 to infinity. Okay, so the upper limit for this will be e to the power of 0, minus the lower limit will be e to the power of minus infinity. Okay, that should be the case. Plus, for this, we will have upper limit will be e to the power of minus infinity, and the lower limit, this minus will come here. So let me keep minus here. Then the lower limit I will have minus e to the power of 0. Okay, that should be it. That should be the case, and I would like to close it, and this is equal to 1. So immediately this is a squared by 2 alpha. So this will give me 1. This is 0. This is 0, and minus minus will be plus. 1 will be equal to 1. So this implies this 2 and this 2 will go. So what will be alpha a square? A square will be alpha, so a will be under root of alpha. So as you remember, alpha is a positive constant. So we can write down the wave function here for the two regions. So what we will have, so a is obtained using normalization condition, and we can write down the normalized wave function. Normalized wave function. Okay, how can I write it? So it will be here, so psi of x will be, yeah, it will be under root of alpha e to the power of minus alpha x for x greater than 0, and psi of x will be under root of alpha e to the power of alpha x for x less than 0. So this will be the set of normalized wave function that will exist between x greater than 0 and x less than 0.